All right. So what if equations are hard to solve without, guessing? How do we solve equations? How do we find solutions without guessing? So if you look at the equation x plus 2 equals 5 and its solution x equals 3, I want us to think about the equation x equals 3 as a way to state a solution. This is basically a statement of the solution. So if I look at the two equations and compare them, then look at the expression on the left compared to the expression that we want in our solution. And is there a way that we can think about how to manipulate and see the difference in that composition of those expressions? So instead of thinking about how to translate an equation to find the solution to an equation, we're going to think about what our compositional goals are for the expressions in the equation. We're basically going to compare expressions to what we want, which is just x on one side. So when solving an equation, our goal is to manipulate or decompose the expressions on both sides of the equation to a single variable factor on one side. So if you think about it, if I can create an equation where it's just x on one side, which is a single factor, it's one term and there's only one factor of x. If I can manipulate expressions to get that, then I'll have solved for my equation because I have the statement of the solution, x equals. So in order to do this, we need to know a little bit about how we can work with equations. So the compositional properties of equality. If we just think of think of the expressions in an equation as weights on a scale. So this is my little interpretation of a scale. I got an expression on the left and an expression on the right. Those two values must always be equal. So what can you do? Well, we can manipulate it. As long as you add the same weight to both sides, the scale will remain balanced. So if I took this expression value, maybe it's like 5 pounds, and I added 2 pounds to the left side and 2 pounds to the right, because it started out equal, the scale would still be balanced. So one of the ideas is we just want to make sure we keep the balance of the equations, right? It's just a way of thinking about manipulating an equation. So it does talk about expression values. As long as I don't change it, I'll be fine. So in terms of composition, we have two different components that make up expressions, which are terms and factors. So in terms of composition, the first one basically says we can attach the same term to both sides. So if we attach the same term, then the equations stay balanced. They have to be the same though. And the second is our other component is factors. We can attach same factors to both sides. So as long as we attach the same thing to both sides, our equations will remain in balance. So how do we take advantage of this to accomplish our goal of isolating x on one side, right? So our goal to solving is to isolate x on one side. That's another way we can explain the composition of just one variable factor x on one side of an equation. So let's look at, and again, I'm sure you've seen equations like this, but in terms of composition, how do we think about it? So if we're solving, then our goal is to have x by itself on one side. So instead of, I want to think about this in terms of composition. So what we do is we look at the composition of the expression with x in it. I notice that this composition has two terms. And if I compare to what I want, then this -3 is an extra term that I'd like to get rid of. So we know we can attach a +3 term. If we attach a +3 term, notice these are opposite terms, and those terms will go away. It'll be 0, and I'll be left with just x, which is my goal. So as long as I attach the same term to both sides, the equation remains balanced. So if I do this, then I get x equals 10, and x equal to 10 would then be my solution. All right, so we're comparing the next equation. If you think of our goal to solving, is to take this expression and manipulate it so it's just x on the left side. So when I look at this composition of our expression, I notice that the composition is one term with two factors. So this 3 is an extra factor. So in order for me to get rid of that extra factor, I need to create a fractional factor of 1. I want to attach a factor of 3 in the denominator so that those factors will cancel. So you can kind of think canceling, taking advantage of those fractional factors of 1. As long as you attach the same factor to both sides, then you can keep the equation equivalent or the same, balanced. 15 divided by 3, or canceling 3 and 15, leaving a 5. So the answer is x equal to 5. Is our solution. So now we don't have to worry too much about how we do it, but the composition tells us what we need to do. So when we have equations that have numbers that are a little more complicated, it doesn't matter. Our goal in terms of composition is still the same. I want to get x by itself. I need to compare that to the expression on the left in this case, and I notice that this expression has an extra term that I'd like to get rid of. So I'm going to attach an opposite term, right? Use opposites to get rid of term values. Well, that means I need to attach a -1/2 to both sides. And a -1/2, when I attach it to the left, I'll be left with just x because those term values will zero out. They're 0 pairs. But 1/3 and -1/2. Well, I know I need to do that. I need to combine 1/3 and -1/2 to get my answer. So we get a common denominator of 6. So multiplying the 3 by 2, the top and bottom by 2, I get 2/6 minus multiplying the denominator by 3 and the top by 3, I get -3. So 2/6 minus 1/6 minus 3/6 is -1/6. So the answer would be -1/6. But the composition of the equation is the same. I just might have to do some side work or some work in your head to combine those numbers. It doesn't matter what type of expression I see, my goal is always the same. I want to get just x by itself. I want to compare that to the expression I have, and I notice that this expression has an extra factor of 2 in the denominator. So if I attach a factor of 2 in the numerator, I'll be able to cancel those and get just x. That just means I need to attach a factor of 2 in the numerator on the right. So x equaling 14 would work here. So what happens if I have a big fraction as an extra factor? Again, I want to get, my goal is to just get the variable by itself on one side. So if I look at the composition of my term or my expression on the left, it has this factor that I need to get rid of. So we know that when we apply or multiply reciprocal factors that they will cancel and leave just one. So what we're going to do is we're going to attach a reciprocal factor of 4/3 to both sides. And this is a factor, so I'm using red, I'm multiplying. I know that the reciprocal factors on the left, negative times negative is positive, and everything cancels, leaving just a. And now I need to calculate negative 1/8 times negative 4/3. So again, I'm going to use canceling to do that. The negatives are gone. The 4 in the numerator will cancel with 8 in the denominator, leaving a 2. So I'm left with just 1 over 2 times 3 in the denominator, which is 6. All right, so manipulating equations in terms of composition. Our goal is to always get the variable by itself. So we look at what and we can do to manipulate our expression. If we have to get rid of a term, then we attach the opposite term to both sides. If we have to get rid of a factor in order to achieve our goal, then we attach a reciprocal factor in order to cancel.